All right. In principle, I think we can start. So at least my watch, my clock shows that it's 3 p.m. Moscow time. So I'm really glad to see everyone, especially the speaker. And well, it's good afternoon to European part of Russia, to Europe, and good evening to Ural region, to Siberia, to far east part of Russia, and good morning to those who listen us from United States. So today we have Nicola Spaldin as a speaker. She's a brilliant scientist and very well known because of various contributions, say from multiferroics, from magnetism, from transition metal oxides physics, and so on. Really a lot of topics she covered already. So let me, but Daniel Homsky, who is the chair today, so he will introduce Nicola. While I want to remind you some basic rules which we have in our colloquium. So first of all, please mute yourself while Nicola is speaking. Then how to ask the question. There is, you see, there is this button chat. So you can write your question there or raise a hand or ask for permission to ask, and then the chair will give you a word or read out your question. And then, today we also have YouTube live streaming. So if you prefer to use YouTube, you can watch us by YouTube. The link is on our website. But YouTube translation is a little bit kind of delayed, I think about 5 to 10 sec. And the last comment is about break room. So after Nicola will finish, we'll ask her to go to breakout room and for some private communication, for maybe it would be better to ask some for some details, to ask some questions there. So that's it. And let me also remind you that we have 2 questions time. Some urgent question can be asked after 15 or 20 minutes of talk. Daniel probably will interrupt Nicola, or she will do it by herself. And a couple of questions can be asked at that time. And finally, after the talk, Nicola will take other questions. So that's it. Daniel, please
Okay.
go ahead. And Nicola could probably share the screen.
Okay. First of all, again, welcome to everyone for the second meeting of our colloquium. So today is a talk of Nicola Spaldin. Serena already told you something about her, but I will maybe tell you a bit more. She is right now, she is professor in Zurich in Switzerland, ETH. That's Eidgenössische Technische Hochschule. That's actually Polytechnical University. That's a very famous place. That's actually, here you see actually the building. That's definitely the best scientific institution in Switzerland and probably one of the best in the world. Also with very important history, because Albert Einstein, in Russian it's Albert Einstein, he actually was a student, graduated from this institute, and then he was professor here for some time. And then later on, Wolfgang Pauli was for many years professor in this ETH. Now, Nicola graduated from Cambridge, from England, from UK, but then she moved to America, to United States, and I got to know her about 2000 when she worked in University of California in Santa Barbara. Very good place, but still about 10 years ago, she decided to move back to Europe in a sense. So she became a really professor in this ETH, and she has now a very active group there, very good young people, and extremely active and extremely productive. So she is, as Sergei told already, she is one of the best experts in the physics of transition metal oxides. and transition metal compounds in general. Not only transition metals, but also some other materials. And she's very famous for her contribution to the field of multiferroic. She's till now one of the main players in this field, but she's much broader actually. She also worked on some multi-layers and many other topics. I don't really know what she chose to speak about today, but I really looking forward to it. Now, what else can I say? That she has very diverse interests actually. Besides science, she is just playing music, but she is also very devoted rock climber. And that's, I don't know whether it plays any role when she decided to move from California to Switzerland. Maybe it did, I don't know. Nicola may tell me, because there are some mountains in California, but of course the mountains, the Alps in Switzerland are much better. That's now, once again, just Nicola, welcome to Russia. Unfortunately, this time is only online, but I hope that hopefully in not so distant future, you will be able to come really in real life to Russia and then visit not only Moscow and St. Petersburg, as people usually do, but also go to Siberia. For example, I can really recommend you to go to Krasnoyarsk because one of the most famous places for rock climbing are what we call Krasnoyarsky Stolby, Krasnoyarsk pillars. That's one of the best places for rock climbing. So that may be also good. But they also have very good physics, actually, in Krasnoyarsk, so you won't lose your time.
Very good.
Yeah. In any case, welcome once again. I'm looking forward for your talk. And I only want to add a little bit to this Sergey general comment about asking questions. You can ask questions by writing some questions in chat, but you can also raise hand, but that's done if you click on link participants. And then there is option. There is an option raise hand. So you can use both, either just raise hand linking in participants, and you can also ask your question in chat. And once again, I really ask you to mute, to turn off, выключить ваши микрофоны, turn off your mics, because it's rather annoying if there is some background noise. Anyway, that's it. And then, Nicola, you are welcome. And we are looking forward to your talk. And please just find a reasonable time, maybe after some introduction in about 10, 15, 20 minutes, so that people could ask first urgent questions and then just go on. Okay?
Sure, of course. Thanks, Daniel, for the very kind introduction. I'm also happy if people would like to ask questions as I'm going. If something's not clear, go ahead and type it in the chat or raise your hand. I might not see it though, because as you can see, I'm at home and I'm presenting from a rather small laptop. So maybe Sergey or Daniel can interrupt me if they see there are a lot of questions or something's not clear. So it's really a pleasure to be here virtually in Russia. It would be even nicer, of course, to be really visiting and have more opportunity to discuss with you all and learn about the exciting science you're doing. But this is a good substitute, a good compromise. Daniel asked me to speak about transition metal oxides, which is, of course, a very, very broad topic. So I had to make some selection and talk about just a very narrow subset. So let me start by recommending, for those of you who want to know more, the book by our session chair, Transition Metal, actually it's even broader than Transition Metal Oxides, Transition Metal Compounds by Daniel Komsky, which has in it, I think, absolutely everything you will ever need to know about this topic. Okay, so let me start by answering a kind of obvious question. Oh, I should also add, I've kind of aimed this talk at kind of beginning graduate student level who may be in any kind of area of physics. So if anybody's really not understanding, do shout up. It's not supposed to be, if I've got the level wrong, then let me know. Or if I'm saying something that everybody finds very obvious, also let me know also. So that was, I tried to make it accessible for most PhD students in condensed. Okay, so what are transition metal oxides then? So they're, of course, oxides, so compounds with oxygen and with transition metals. And the transition metals, of course, are this group in the middle of the periodic table that are characterized by having as their outermost valence electrons the d electrons. That's what defines a transition metal oxide. And there are 3 rows of them that we discuss as transition metal oxides, which we label by their outer D shell, the 3D, 4D, and 5D transition metal oxides, all of which are very interesting. I will be focusing today mostly on the 3D transition metal oxides. So these are compounds formed by this block in the periodic table with oxygen. And why are transition metal oxides interesting? Why, when Daniel picked one topic to talk about, did he say it should be transition metal oxides? Well, so there are very, very many reasons. The first one that comes to mind is that they're abundant. They're materials, if you're thinking about trying to come up with new materials to make devices that will be widely used, you don't want to pick an element that's extremely rare. And if we look at the abundance of the elements, oxygen, of course, as this is a plot here of the abundance of the elements normalized to 10 to the 6 atoms of silicon versus the atomic number. So it's just going straight across the periodic table. And the most abundant element is oxygen. So for making oxides we're never going to run out of oxygen. Or if we do run out of oxygen, I guess we have other problems apart from making our transition metal oxide. The 3D transition metals are here. They're all above 1, and anything above 1 is considered appropriate for device applications. So with transition metal oxides, we don't have a problem with running out of material. I found this plot very interesting because the rare earth elements are also not particularly unabundant. So it's not really an issue to have enough rare earths. There's issues, I guess, with distribution of the rare earth availability around the globe and purification, but they're not lacking in abundance. Some of you may be very interested or be working on iridates, or maybe particularly theoreticians. I think for experimentalists, iridates are extremely expensive. Iridium is the least abundant stable element. So this is a 5D material, so it wouldn't be a good choice in terms of abundance, but the 3D transition metal oxides are all rather abundant. They're non-toxic, which is good if you have to do work in the lab or if you want to make devices. I always think I'd rather, of course, be in the oxides lab than the arsenic lab if there's a big fire on campus, at least when I was in California, and this was always an issue. In terms of so that was kind of practical issues. In terms of the chemistry, transition metal oxides are very diverse in terms of the kinds of elements that can be incorporated, the kinds of chemistries, in terms of their structures and dimensionalities. So here I just show 3 examples. This is a Pyroclaw structure. It's a 3-dimensional structure, and it leads to interesting physics because you see it has transition metals that are in octahedral coordination. You see this little octahedron here, which represents the oxygens around the transition metal, and also transition metals that are in tetrahedral coordination that are connected together. So this diversity of connectivity can lead to interesting behaviors, particularly, for example, magnetic and structural frustration. Maybe you recognize this structure on the right. This is the prototypical high TC cuprate superconductor, which is a layered 2-dimensional compound. The transition metals in this case are at the center of these coordination polyhedra, which are square pyramids. So again, another kind of local structural motif around the transition metal. Again, the oxygens are the little red dots here. And then the structure at the bottom, which is actually the structure I'll probably discuss most today, is the perovskite structure, in which the transition metals, in this case, are octahedrally coordinated by oxygens. So they're in an octahedron of oxygen ions. And these octahedra are shared together at the corners, forming a 3-dimensional network. And then there's another different cation filling kind of the holes in between. So of course, this diversity in the chemistry and the structure and the dimensionality can give us a very wide range of physical properties. From a physics point of view, there's 2 aspects that make transition metal oxides particularly interesting. One is coming from the transition metal and one from the oxygen. And from the transition metal, these d electrons, which we know are rather localized electrons, they're rather tightly bound to the ionic, to the nucleus, to the ion. They're not, unlike s electrons, which are rather large and floppy, the d electrons are kind of close in to the nucleus. And this fact leads to strong electron-electron correlations. The electrons are kind of very close together, which means that the behavior of one electron really explicitly affects the behavior of the other electrons. They're not just experiencing the other electrons in a mean field picture, they're really strongly correlated and interacting with each other. So that's why the transition metal part of transition metal oxides is interesting. The other part of a transition metal oxide is, of course, the oxygen, and this also is important in making the physics of transition metal oxides really special. And here it's really the electric polarizability of the chemical bond that forms between the transition metal and the oxygen, I put is just right in its response to perturbations like electric fields and for example, changing the bond distance. It's a very polarizable bond. If you look to the left of oxygen in the periodic table where you have nitrogen, then the transition metal nitrogen bond is a very strong covalent bond. And I'm going to, is this being recorded, by the way? Oh, let me see.
Well, yes, actually it is recorded. We are live streaming in YouTube, but if you don't prefer to
okay, no, I was just wondering whether
I
was going to say the transition metal nitrogen bond is kind of boring, but maybe I shouldn't if it's being recorded. But it's very covalent and strong, and you form a bond and that's it. If you go to the right of oxygen in the periodic table where you have fluorine, the transition metal fluorine or transition metal chlorine bond is very ionic. And so it's a very stable ionic bond. I should say it's also very interesting. But the oxygen, which is just in between, it's neither strongly ionic nor strongly covalent. And so it's very susceptible to perturbations. And this combination of the two properties, the strong electron-electron correlations, lead to strong responses, in particular to magnetic fields, magnetic perturbations, and the polarizability of the oxygen bond leads to strong response to electric fields. And so this combination, transition metal sulfides or other transition metal compounds are just not, don't have quite the richness, I'd say, of the transition metal oxides. And then I think this is the last point I wanted to make about why transition metal oxides are so interesting. And that's that we know that that block of transition metal ions can adopt many valence states. For example, it's common to have ion 2+, ion 3+, it's even possible to get ion 4+, and so on. And because the valence states of the transition metal ions are so flexible, the defect chemistry is very rich. For example, we can take out an oxygen and the oxygen will leave its electrons behind. And that's not a very energetically expensive process because the transition metal can readily change its oxidation state. So the defect chemistry can be very rich. And here's just an example on the left. This is perhaps the simplest complex oxide. It's strontium titanate. It's a crystal of strontium titanate. And in the bottom picture is just an optical, just a photograph of this crystal of strontium titanate. Sorry, I didn't put the scale on here. I shouldn't say without oxygen vacancies, with a very low oxygen vacancy concentration. And in the upper picture, this crystal's been annealed in nitrogen in a reducing atmosphere, so it has a lot of oxygen vacancies. And you can see right away that the optical properties change completely, changes color. This is a very dramatic change. And on the right-hand side is a high-resolution transmission electron micrograph of this time a thin film of strontium titanate, which has been treated to be oxygen rich, so almost stoichiometric. And in the upper part, it's been grown in an oxygen poor environment, so it has many oxygen vacancies. And the properties, the upper part is conducting and the lower part is rather insulating in this case. So this again adds to the richness of transition metal oxide behavior. So let me just summarize, or another way to think about that is that the relevant energy scales in transition metal oxides are all very similar to each other. And this leads to either coupling or competition between them. So for example, the Coulomb repulsion that comes from the electron-electron correlations is usually of the order of tenths to an electron volt. The widths of the bands, which is coming from the bonding between the oxygen and the transition metal, is similar to the Coulomb repulsion. Crystal field splittings, the interaction between the oxygen ions and the energy levels in the atom, are also of a similar energy level. Strain energies that can occur in the lattice through spontaneous internal distortions or from external perturbations, also are the same energy scale. And the Hund's exchange, the tendency of the electrons to align with their spins parallel is also can be of a similar energy scale. And so all of these interactions between electronic and spin and orbital and lattice contributions are very similar, which leads to a very strong tunability, sensitivity of transition metal oxides. So for example, the coupling between the electrons and the lattice, this manifests in very large dielectric constants. If I apply an electric field, the system will polarize a lot because there's a strong interaction between the electron and the lattice. Also ferroelectricity, which we'll come back to, large thermopower, so good thermoelectric behavior. And I guess it's a little bit controversial whether high TC cuprate superconductivity probably also certainly has an electron lattice interaction component. Between spin and orbital, then we have properties like piezomagnetism, magnetic frustration, non-trivial topology, which I won't touch on today, but of course is an extremely exciting current topic. And then interaction between the electrons and the spins, and I put lattice also in brackets here. Properties such as multi-Furrowism, magnetoelectricity, so electrical response to a magnetic field and vice versa, magnetoresistance, change in conductivity with magnetic field and spintronic behavior, all are result from this strong electron spin coupling. And then lattice orbital, maybe Daniel has some more ideas here. Here I was struggling a bit. There's some discussion about what's called Orbitronics, where, for example, here's a sketch of kind of an orbital lattice coupling where there's a distortion of the lattice, which determines which chemical orbitals are occupied. And there's some discussion that one could maybe then have a kind of conductivity of these orbitals through the lattice and do maybe information processing with this. I put a big question mark there. I'm not so sure exactly how that would work. And also kinds of hidden order, that there could be kinds of orbital ordering that we don't really yet know how these manifest. But I think this is perhaps still the kind of corner of this diagram that has a lot of open questions. Okay, so one more example then, which may be familiar to many of you of how this fact that the spin and the orbital and the lattice coupling have very similar energy scales, so that when you make a small energy change, maybe you apply a field, you dope, you strain your material, you could tip the balance between these competing rather large energy interactions, electron volt energy scale interactions, and hugely order the ground state properties. And this is the plot it's the phase diagram of the high TC cuprates and also many other exotic superconductors, showing temperature as a function of, this would be hole doping in the cuprate superconductors, and showing that as we change the hole concentration, we change very drastically the behavior from an anti-ferromagnetic Mott insulator at 0 doping through the superconducting dome to kind of Fermi liquid-ish behavior at very large hole doping, through conducting regions that are non-Fermi liquid and phases that are really not understood. For example, the pseudo-gap phase, even what's ordering here. Good. So that's kind of my introduction generally to transition metal oxides. I'm now going to focus on a particular class in this kind of scheme, which is the kind of electron spin lattice group, and in particular multi-Ferroics, which Daniel mentioned have been very close to my heart. But if there's any general questions about just transition metal oxides in general, I'd be happy to take them now, or I can give you a little bit of the multi-Ferroics background before we have a discussion.
Yeah, so everyone can ask a question now. If you want, you can simply just raise a hand. I don't know, Sergey, you will just take care of it, because I don't know how does it work really.
Or I'll stop in again
in any case, actually, you can unmute. Maybe just we can make it even simpler. Maybe you simply can unmute your mics and ask a question. And I hope there will be no big crowd.
Chaos. Or else, and I'll stop again in 5 or 10 minutes if there's no questions yet.
So if anyone has a general question on this introductory part, then you are welcome to ask. If not, we just go on and then Alan raised hand. Okay, just.
You should unmute yourself.
Unmute yourself and ask question. Yeah.
Hello, everybody.
Yeah, it's okay. You can speak.
Nice introduction. So my question, because I'm not from people who are doing HANS, you know, that's rule on materials. May you say what is the typical compounds for such materials?
Yeah, so I'd say any combination of any of the transition metals with oxygen, I'd say most of them can be combined together. Okay. So the one that I showed already, strontium titanate, is a compound of strontium, titanium, and oxygen. And now we look at more examples. That the high TC cuprates, for example, are yttrium, barium.
Really? Oh, okay. I never think about that. Okay, but yeah, okay, yeah. Thanks.
Okay, then we have Valentin Davidov.
No, I'm just getting interference.
Your mic doesn't work properly, Valentina. I'm sorry, but we don't hear you really. We hear some strange sound. Maybe just check your mic. Doesn't work. Sorry.
Or try typing in the chat, maybe.
Maybe you just write down. Your mic seems not to work properly. Maybe you write your question in the chat. Then we will read it. We will read it.
Or maybe we can go on with multiferroics and then...
maybe just in the meantime, just we go on, and in the meantime, you just can write down your question in the chat, and we will ask you after the end of the talk, okay?
Okay. So let me
okay, go on.
Get a little bit specific then, and as I said, I'll choose one of these kind of competing interactions and discuss in a little bit more detail some materials and some properties. And so the class that I chose to talk about a class which are called multi-ferroics. And these are materials that have some combination of ferroelectricity, which means they have a spontaneous electric dipole moment, a spontaneous electric polarization. And this polarization is switchable by an electric field. That's what this arrow is meaning here. And then another ferroic property that can make a part of a multiferroic is ferromagnetism, which is a spontaneous magnetization that's switchable by a magnetic field. So it has a magnetic dipole that's magnetic field switchable. Or ferroelasticity is another established ferroic property, a spontaneous deformation that's switchable by an applied strain. And so in principle, any two of these combined in the same material is a multiferroic. So for example, a ferroelectric ferroelastic would be a multiferroic. And this actually includes most ferroelectrics. Most ferroelectrics, when they have the structural deformation that makes the electric dipole, when they make the electric dipole, they have a structural deformation associated with that. So they're also ferroelastic. Ferromagnetic ferroelastics also exist. The multiferroics that at the moment people tend to mean when they say multiferroic are this combination here, the ferromagnetic ferroelectrics, which are perhaps at the moment the most widely studied. And the reason that the combination of these ferroic properties is interesting is that in addition to having the property switchable by its own conjugate field, so for example, polarization being switchable by an electric field, then in a multiferroic, one has cross couplings. So for example, in a ferroelectric ferroelastic, the application of an electric field will deform the material. And this, of course, we're familiar with as the piezoelectric effect. In a ferroelastic ferromagnet, then the application of it, when it's strained, it'll change the magnetic properties. And this is used, for example, in magnetomechanical actuators or in piezomagnetism. For the ferromagnetic ferroelectrics, then one can, with a magnetic field, modify the electric polarization, and with an electric field, modify the magnetization. And this, it's what's called magnetoelectric coupling, is really a source of interest for ferroelectric ferromagnetic multiferroics, particularly in the direction of being able to do electric field control of magnetism. From a device point of view, this is very appealing because many of our magnetic-based technologies today, they're controlled by magnetic fields, of course. The conjugate field for the magnetism is the magnetic field. But to make a magnetic field, one needs a big coil of wire and to run a current through it. And this is a bulky component and it heats up and it uses a lot of energy. So if one could do electric field control of magnetism, this is appealing from a technology point of view. So this, I put in a little bit of historical background here, because the field of magnetoelectrics and eventually of multiferroics really started in the former Soviet Union and largely in Russia. And in fact, the earliest mention that I've found of the magnetoelectric effect is in this early edition of Landau and Lifshitz Electrodynamics of Continuous Media. The one, well, by the time it was in English, it was in 1959. I think the Russian version is a year or so earlier. And it's interesting, this comment is not in the subsequent editions, but there's this wonderful section. Let us point out two more phenomena. It comes in the section after, you know, magnetic permeability and so on, which in principle could exist. One is piezomagnetism, which consists of linear coupling between a magnetic field and a solid in a deformation, analogous to piezoelectricity. And the next one is the one that's of interest to us today. The other is a linear coupling between magnetic and electric fields in a media, which would cause, for example, a magnetization proportional to an electric field. So this was the first statement that magnetoelectric response should, in principle, be possible in materials. Both these phenomena could exist for certain classes of magnetocrystalline symmetry. We will not, however, discuss these phenomena in more detail, because it seems that up till now, presumably they have not been observed in any substance. So this was the statement in the late 50s. In 1959, Igor Jalashinsky wrote a landmark paper showing, theoretically on symmetry grounds, that such an effect, such a magnetoelectric effect, must exist in chromium-203, was his prototypical example. Igor was, I think, a graduate student of Landau at the time. I think maybe you guys can correct me if I'm wrong. And in the same year, actually, then Astrov demonstrated, he made a measurement of the magnetoelectric effect in chromium-203. So this was extremely exciting. And I guess then they had to take this statement out of the Electrodynamics of Continuous Media book, because it had been demonstrated. And so really the motivation, here's our little multiferroics triangle again, the motivation for trying to make multiferroics, which then continued very actively for the next decades in the former Soviet Union, largely in Russia, was for this magnetoelectric effect. The fact that to be a magnetoelectric, it's not required to be a multiferroic. Chromium-203 is not actually ferroelectric, it just breaks inversion symmetry. But when a material is multiferroic, then it's the case that one has the appropriate symmetry to have this magnetoelectric effect. Okay, are there any other questions? Is that question that was waiting, has it appeared? Or should I just keep going?
There was one general question about the first part. I will read it, but unfortunately I don't see it from whom was it. But I will read this question actually. Similar energy scales in apparently what you mentioned about transition metals should lead to difficulties in standard perturbation theories. Are there general, non-perturbative general theories, or each phenomena requires its own theoretical approach?
So that's a very good question. And so my kind of techniques expertise is density functional theory, so electronic structure calculations, where we really treat the electron interactions at a mean field level. And this is awful for strongly, it's inappropriate actually for many very strongly correlated materials. Techniques that are extremely good for strongly correlated materials, like, you know, full model Hamiltonians, or even, for example, dynamical mean field theories, are not so good at including the chemistry, right? So they can't, for example, incorporate readily the chemistry of a transition metal oxygen bond, or the specifics of, you know, when I really change from manganese to iron, the details of that chemistry changes, and so the behavior changes. And so this of course leads to difficulties in being predictive if we want to design new materials or predict accurately their properties, because the kind of two limits that theories are good at, neither captures both the richness and complexity of the chemistry or the details of the strong electron-electron interactions. So that's a very good point. I guess this real richness of the physics, which makes them have such interesting complex properties, makes them also very hard to describe. For sure. Okay, so that's kind of the history, and as I mentioned, starting from this landmark work on magnetoelectrics in the very late 1950s, this motivated work over, I say, really over the next couple of decades on trying to make multiferroics, which then kind of faded away because it just turned out to be really hard to get good materials. And I'll come back and address why that is in a while. But it was certainly in the former Soviet Union that all of the pioneering work was done. I came along in the late 90s and I got really interested in the material science aspect, the kind of materials chemistry aspect. Why was it hard to make multiferroics and how could we do it? And this was a very exciting time. So I was at Santa Barbara, and as Daniel mentioned, he was visiting often at the Institute for Theoretical Physics. So this is kind of my history of multiferroics. So I would go and chat to Daniel a lot because he was this huge resource. And of course, he knew all of the history of the field. And over the next years, we'd meet very regularly at conferences. And I found that he also knew all the literature in the field, which was very, very helpful. And for many decades, I realized I hadn't actually come up with anything new because everything had already been done in the former Soviet Union. And so for me, my career highlight was about 2 years ago when I was discussing with Daniel at actually the Multiferroics Gordon conference, the last time we were all allowed to travel and meet together. And I was showing him some of my work, and he said, gosh, that's such a good idea. I even checked, and I was surprised that it wasn't done in Moscow in the 50s. So this was a big breakthrough for me. Okay, so let me go back then to the materials chemistry of multiferroics. So why is it hard to make a material that combines ferromagnetism, so it has a magnetic dipole, together with ferroelectricity? Why is this difficult? And the answer to this question is very, very trivial. It's not any profound symmetry question. It's basically just that the kinds of atoms that are good at being magnetic, that make good magnetic compounds, are a different set in the periodic table from those that are good ferroelectrics. And so one has just basically this chemical mismatch between good ferroelectrics and good ferromagnets. And I'm going to try and explain to you why from kind of two sides. I'll start with a kind of hand-wavy chemical bonding picture for those of you who like to think about where electrons go in solids, and then I'll show you the perturbation theory approach. Okay, so the favorable chemistry to be a ferroelectric is that one should be a transition metal oxide, but your cation should be a D0 cation. So it should be in an oxidation state such that it's given up its d electrons. Okay, so this is kind of a statement, an observation. Most of the good ferroelectrics, most of the standard conventional ferroelectrics are transition metal oxides with D0 cations. They have empty transition metal D states. And here's a kind of cartoon of why. So a typical prototypical ferroelectric would be, say, barium titanate. So the transition metal is titanium 4+, which doesn't have any d electrons. It's given up its 3d electrons. It's octahedrally surrounded by oxygen 2- ions, which have filled p shells. And at the corner are just barium 2+ ions, which are closed shell. They're not doing anything with the chemistry. And here's a cartoon, and here it's in its centrosymmetric structure. This is the structure at high temperature. And so it doesn't have an electric dipole at high temperature. It's in the paraelectric state. So here's a cartoon. Here's my oxygen ion, which has got a positive ion core. And then in the 2p orbital is filled with electrons, and it's centrosymmetric. So it's halfway between the titanium 4+ ions that don't have any valence electrons. They're empty shell ions. And this is how it's kind of a cartoon of the electron density in the centrosymmetric state. As the temperature is lowered and barium titanate reaches its Curie temperature, it has a structural distortion into the ferroelectric state, and so it becomes lower energy for this titanium atom to move away from the center of the two oxygens. And this energy lowering, the fact that it's lower energy to move away, is what makes barium titanate a ferroelectric. And from a chemistry point of view, so this is the structure, a bit exaggerated. The titanium moves towards one of the oxygens. There's a bit of a distortion, structural distortion associated with that, and there's an electric dipole. Whoops, sorry. And so chemically, this is an energy lowering process, because as this cation moves towards the oxygen, the electrons that are in the oxygen can spill towards the cation, which doesn't have any electrons in its D shell, and make a partial bond formation. And this bond formation is energy lowering. So the fact that the titanium 4+ doesn't have any D electrons there, it's able to accept electrons from the filled oxygen shell, makes this process of the ion off centering energy lowering. If there was no chemistry, if there was no bond formation, I'd just be trying to push two ions together, and that would be would increase the energy. So the D0-ness of the transition metal cation is very favorable for off centering to make electric dipoles. If you, this is, I'm trained as a chemist, so I like this picture. If you don't like this, it's a little bit hand waving, I know. So if you prefer, you can make a, you couldn't use perturbation theory and expand the Hamiltonian, starting from the Hamiltonian for the centrosymmetric structure as a function of the atomic distortion. So in the cartoon I just showed, this atomic distortion would be the titanium shifting towards the oxygen. In a real material, it would be the normal coordinate. In barium titanate, it's actually really a combination of titanium and oxygen and barium. It's the normal mode that takes you from the pyroelectric to the ferroelectric structure. And so one does a normal perturbation theory expansion in this coordinate describing the ferroelectric distortion. H1, of course, is the first order correction, which is just dH by dq times q. And H2 is the second order correction, which is d2h by dq squared times q squared. Well, sorry, H2 is just the d2h by dq squared part. And so then the energy in a perturbation theory picture as a function of the distortion is the starting energy plus some first order term. And this first order term is what gives us the so-called first order Jahn-Teller effect. This one's not relevant for ferroelectrics because it's only non-zero for degenerate states and when Q is a symmetric distortion. So that one is not determining whether something's ferroelectric or not. The second set of terms decide whether something is whether it's energy lowering for a system to make a ferroelectric distortion. And let me, oops, sorry, lost my mouse. There we go. Let me show you what these mean. So the first order term again is describes the regular first order Jahn-Teller effect. It's non-zero for orbitally degenerate states, and it's a centrosymmetric distortion. This second two pair of terms is sometimes called the second order Jahn-Teller effect. And if this is energy lowering, then our system, it's favorable energetically for the system to become ferroelectric. And the first term is always positive, and it corresponds to moving the nuclei without letting the electron density change from the zeroth order system. You see that the wave function stays in its zeroth order undistorted state. We try to push the ions towards each other, but we don't let them rehybridize. And so this is energy raising. And so of course we want this term to be small. The second term, which is negative, so this term we'd like to be large, it's going to lower the energy. And this is the term mathematically illustrating or describing that rehybridization of the electrons we just looked at in the cartoon. This we want to be large, and because the perturbation is odd symmetry, we want to make it's a polar distortion, we need to have the ground state and the first excited state to have opposite parity. So we need a non-zero matrix element in the numerator for the denominator and when the denominator is fairly small. And what this means in particular is, for example, I can't have the ground state and the first excited state composed entirely of d electrons because they have the same parity. So let me show you what happens in a typical ferroelectric, and then I'll stop maybe for questions. So here's, I've written out these two terms again. The first term we'd like to be small, and of course this is going to be small if I don't have a lot of valence electrons. If when I push the ions towards each other, there's not a lot of repulsion. So if I have a d0 electron density, then this first term is small. The second term is going to be very negative and therefore favorable if my ground state and my first excited state have different parity. So again, here's the case of barium titanate, the prototypical ferroelectric, and I'm plotting here the density of states as a function of energy, still in the centrosymmetric structure. And what you see is that the top of the valence band is made of oxygen 2p states, and so it has odd parity. The bottom of the conduction band is made of titanium D states, and so it has even parity. And so because I'm hybridizing here between oxygen and titanium states, then this matrix element is non-zero, and I have a large energy lowering when I move my when I make my distortion. You see this in the density of states in the lower panels here. When I displace the titanium, see how the density of states changes from the centrosymmetric case. The bottom of the valence band is shifting down in energy and hybridizing strongly with the oxygen. So this is yet another way of seeing the kind of cartoon picture I showed just before. Okay, so that's the message from that is to be a good ferroelectric, we should have a D0 cation. Of course, you know that to be magnetic, we said at the start, if we want to have magnetism, then we want localized electrons in partially filled orbitals. And so to be a good magnet, my transition metal oxide should have partially filled d orbitals, which is then chemically contraindicated with the requirement for ferroelectricity. Are there any questions on this aspect? Otherwise, I'm going to, next I'll go on and look at actually some examples of how one can overcome this contraindication between ferroelectricity wanting D0 cations and ferromagnetism wanting partially filled d orbitals, dn cations, non-D0.
Okay, I can ask. I just understood that I never met ferroelectrics based on F systems, but maybe there are some. So could you comment on this?
So that's gonna be one of the examples I'm gonna give actually. So we'll look at the case. So if we look here again at our, if I look again at, here's the barium titanate, the D0 titanium in the center, and barium 2+ in the corner. If I replace this barium 2+ by an F electron system, a rare earth, and we'll look at the case of europium because this is a good divalent rare earth, then of course I can keep the ferroelectricity of the D0 transition metal cation and combine it with F electron magnetism from the europium. So absolutely. So that's going to be one of the strategies that we've used actually. Yeah.
I have a question. Can I ask?
Yes, please.
Yeah, it's Igor Sandalov, Stockholm. The question is to the same basket, but according to your speculations, in better candidate would be lanthanum or cerium, because one is F0 and another F1 with very low, very shallow level. Isn't it?
Aha, so you're thinking of the effort. So, okay, so I was answering the previous question by saying I was going to keep my D0 cation for the ferroelectricity and use the rare earth as the counter ion for the magnetism. So you're thinking of using the lanthanum as the ion that off-centers. Yes, so there was so for example, lanthanum 3+, then the empty cation. So the bottom of the bottom of the valence band would then, I think, be lanthanum P, right? Because it's the no, lanthanum D. And so in principle, the second Odion-Teller effect should work, I think. But I think the size would be too big, right? One would have to have a different coordination. Daniel, do you know of any materials where the lanthanum is off-centering being the active ferroelectric ion? I don't know of any examples. And it might be that it's just too big. You know?
But in any case, probably it would not be due to F0.
No, it would not be F0.
Probably that was actually the question, because instead of say D0, maybe you could have used F0, but covalency of F electrons with oxygen or whatever, it's very weak.
Yeah, and it'd be very higher up in energy. So, yeah. So
F electrons are not useful for that, I think.
Right kind of philosophy, though, absolutely. Yeah.
Okay, thanks.
You're welcome. Okay, so let me show you an example then. Whoops, sorry. Okay, so the simplest possible way then of making a multiferroic, and I should say there are now very many clever ways. Daniel has really introduced some. I'm going to give you one, and if there's time, maybe two examples of just really non-clever ways of designing a multiferroic. And that's basically by just combining the chemistry. So taking a transition metal with its d electrons and then introducing the ferroelectricity in a different way than using a D0 cation. And here the example I want to show you is bismuth iron oxide, bismuth ferrite. So the iron is giving us the d electrons. It's iron 3 plus it's D5, so it's very, very magnetic. We have the oxygen, which is because we're looking in the transition metal oxides. And then the bismuth, in this case, is providing the ferroelectricity. And okay, this is the structure. It's perovskite structure, so the iron is octahedrally coordinated by the oxygens. The bismuths are at the corners of the unit cells. And the bismuth, trivalent bismuth, is ferroelectric because it has a pair. If we take 3 electrons out of bismuth, it has a pair of 6 s electrons, which is stereochemically active. This lone pair forms a localized, rather than staying a spherical like 6s in a sphere, it localizes on one side of the bismuth and makes a dipole, just like, actually this picture is ammonia, right? Just like the lone pair of electrons on the nitrogen in ammonia, the 6s electrons on the trivalent bismuth localizes it. Of course, it mixes in some p character to do that and makes a dipole. It's negative, the bismuth is positive, and so it introduces a dipole. So we're basically exploiting the fact that in transition metal oxides, there's this richness of chemistry that, and more than one place to put cations. So one can have 2 different cations, one of which is going to be providing the magnetism and one of which is providing the ferroelectricity. So bismuth ferrite was not a new material when we started working on it. This is a picture from the 1980s of a beautiful single crystal from the late Hans Schmidt, who's in University of Geneva. It's a rather large crystal. You can see that it's very pretty. It has a name. This crystal is called Fern for obvious reasons. These striations that you see here are the result of twinning, and the black color is because it really has a lot of defects. And so this was a beautiful sample of bismuth ferrite, but it was not possible to demonstrate in this sample that it was actually multiferroic. For example, ferroelectric switching could not be achieved. So in the early 2000s, the real breakthrough came from abilities in synthesis, and in particular in thin film growth. And here's a high resolution transmission electron micrograph grown in the group of Ramesh, the microscopy from Marta Rossel. The white dots here are the bismuth atoms. The very faint white dots are the iron. And you can see that this is a thin film and it's really, really perfect. So this advance in materials synthesis, in particularly in thin film growth, was really what allowed the properties of multiferroics to really be demonstrated. Okay, and so remember the question that we set out asking ourselves was, well, first of all, could we make multiferroics? And can we control the magnetism with an electric field? And so I want to show you, this is the very first data. This is from 2006, where we demonstrated, again, this was in collaboration with the group of Ramesh, that one could control the magnetism with an electric field. So I chose these data because it's really the very first time that we were able to do this. It was very exciting. So this is a picture of looking at the surface of a film of the kind that I just showed you. And it's the same area of the surface imaged in two ways, one using piezo force microscopy and one using photoemission electron microscopy. And this is just an as-grown sample before any electric field is applied. The piezo force microscopy is sensitive to the ferroelectric domain. So this is indicating the brown and the white colors are indicating opposite orientations of the electric dipoles coming out of the surface. And the photoemission electron microscopy is responding to the magnetic domains. So the gray, light gray and dark gray is indicating opposite orientations of the magnetic order parameter. So this is before any electric field was applied. And what I want you to notice already is that the pattern seen in the piezo force microscope is the same or has very many similarities to the pattern seen in the photoemission electron microscopy. So for example, you see this kind of fork shape here, kind of U shape. We see it up here. I'm sorry, I couldn't hear that. Can you repeat that question? Oh, no, maybe it was just a background noise. Just a background noise, okay. In interest of full disclosure, I have to be completely honest here and admit that bismuth ferrite is actually an anti-ferromagnet. So what's being seen here, imaged here, are the anti-ferromagnetic domains. So it has these very large local moments on the ion, but they anti-align. So it's not ideal in terms of what we would like for a multiferroic. But so these are the anti-ferromagnetic domains. Clearly we have this coupling, right? We have a coupling between, or correlation between the electric dipoles and the magnetic dipoles. Okay, so let me show you what happens when we apply an electric field. So this is after an electric field is applied, and in the piezo force microscopy, I want you to just see that we see something different. So domains have been switched. In this very first experiment, they were not switched very nicely or uniformly, but there's now a different pattern. And in the photoemission electron microscopy, they also switch, and they switch to the new pattern. So you see this kind of dagger here. It's like a dagger here. And in particular, let's highlight maybe one spot that was white at the start and is now brown in the ferroelectric domains. And the same spot was dark at the start and is now light in the magnetic domains. So this was really very exciting.
Excuse me,
Yes?
What is the scale of that images?
Oh, did I not have it?
Presumably microns, right?
Yes, it's some number. I'm guessing this is about 10 microns or larger. Sorry, yeah, I'd have to take a look. I apologize that that somehow got chopped off. Yeah, sorry about that. Yeah, this is macroscopic. Yeah.
So it means that is not really. This means that is not really evidence that is anti-ferromagnetic, because it can be also ferromagnetic, right?
So from these data, the particular way that the PEM was done, it was sensitive to the anti-ferromagnetic domains. And from other measurements, it's known that bismuth ferrite is anti-ferromagnetic. It's a bit unfortunate. We'd be happier if it were ferromagnetic, but it's not. So what's going on? So how does this electric field control of the magnetism work? So here's a picture of the bismuth ferrite again. It turns out that the electric polarization is in the diagonal direction, the 111 of these perovskite cubes. And the easy plane for the anti-ferromagnetism is perpendicular. It's the 111 plane. So the magnetic moments are lying in this easy plane. It's actually rather isotropic easy plane. And if when I switched my bismuth ferrite, I switched the electric polarization from this top right diagonal to the bottom left diagonal. So if I did that, in fact, the magnetism would not switch. It would stay in this easy plane, and it wouldn't care. There's nothing symmetry-wise that would even ask it to change. The ferroelectricity would just go in and out the other side, and it wouldn't be affected. But what happens, this is a thin film, and the orientation of the film, it's like grown, so the bottom is the kind of bottom of the page, and it's grown in this 001 direction. And so when I apply an electric field, it's applied just in the down direction. The polarization starts off net in the up direction. I apply an electric field in the down direction. And what happens is that the polarization doesn't go straight through to the other side. The structure gets distorted, so the polarization switches from one corner of the unit cell to the next one, goes by 71 degrees, and then another corner around again, and eventually makes it to the other side. So the elastic deformation associated with the electric polarization moves around as the polarization goes from one corner to the other and out to the other side. And so look at what happens to the easy plane of the magnetization. And it starts perpendicular to 111, then it rotates, so it's perpendicular to the new polarization axis, and then the magnetism has to come with it, right? The new easy plane of magnetization has come around to here, then it rotates to perpendicular to the second intermediate axis and ends up rotating all the way around. So the switching of the magnetism is not really I'd say it's a kinetic process. It's not really a thermodynamic process. The magnetism doesn't care. It wants to be in this plane. It doesn't care whether the polarization is here or here. But during the switching process, it gets dragged around. So if you like, this is not, you could argue it's not really a magneto-electric effect. It's a magneto or electro-elastomagneto effect in this case. We were anyway really excited. We were not the only people who were really excited. This intrigue of electric field control of magnetism was featured as one of the breakthroughs of the year in Science magazine. And since then, it's really been built on a lot. And just last year, I'd say really the first prototype multi-ferroic devices have been announced by Intel. It's perhaps a little bit of a bad sign that they published this paper in Nature rather than keeping very quiet and patenting it in terms of their opinion on the future of multi-ferroic devices, but it was at least very exciting to at least have a prototype.
This Intel device using bismuth ferrite or using something else?
It's using bismuth ferrite exchanged coupled to, I think, cobalt, and then that forms the, and so they exchange bias cobalt onto the top of the bismuth ferrite, because then they introduce the ferromagnetism. So when they switch the ferroelectricity, they also switch the anti-ferromagnetism in the bismuth ferrite, which then switches the ferromagnetism in the cobalt. And then that part talks to a kind of spintronic device, which then converts back into a kind of current basis. So it's very complicated, actually. Yeah. But it uses bismuth ferrite. Yeah.
Great.
If this transition is discontinuous in electric field or not?
The transition, the switching, or the
threshold in electric field when it happens. Transition.
Yes. So the hysteresis and the coercivity is very sample dependent. I'd have to look at the actual data, but yeah, it's certainly hysteretic. Absolutely.
Mm-hmm. Thank you.
Yeah, there are also two questions in the chat. Maybe I will just ask you, interrupt you for a moment. First question was from Fabio. How exchange and super exchange interaction comes into play in these properties? I mean, probably in multi-ferrite properties. It was asked some time ago.
Yeah, so in the bismuth ferrite, of course, the oxygen-ion interaction is the strongest magnetic energy scale, and it's D5, almost 180-degree super exchange. So it's a really, really robust anti-ferromagnet because the super exchange is the dominant interaction. I'm not sure if that answers the question or not. So the exchange or the super exchange is determining the certainly determining the type of the magnetic ordering.
And the second question, which is written typed, but unfortunately I don't see from whom is it. I'm sorry for the after. Is there antiferromagnetic domains? If there are antiferromagnetic domains in bismuth ferrite, what is causing the energy gain in this sample? It cannot be magnetic stray field as in ferromagnetic sample. Can I find out what energy is favoring domain formation?
Yeah, no, this is a very good question. And so you could argue, in fact, another way to think about what I was explaining here is that the coupling is between the anti-ferromagnetism and the ferroelectricity is caused by the domain walls, actually. I mean, it would be an alternative viewpoint. And maybe it's easy to see in this picture. When I have a ferroelectric domain, then my anti-ferromagnetic plane is the plane perpendicular to the polarization. And within that ferroelectric domain, you're absolutely right. There doesn't have to be any anti-ferromagnetic domain walls. Maybe there will be some just kind of by chance, but there's no energetic reason for there to be an anti-ferromagnetic domain wall. But then when I have a ferroelectric domain wall, say between this orientation of ferroelectric polarization and let's say this one, then my easy plane of anti-ferromagnetism has changed. And so I have I don't know if you'd call it really an anti-ferromagnetic domain wall, but a discontinuity in the anti-ferromagnetism because the plane in which the magnetic moments are oriented has changed. And so that's what's being picked up by the PEAM, that the whole easy plane of anti-ferromagnetism has changed. And so I guess you would say the L vector changes with it. But you're right, within a single, and I think that's what we were seeing here, is that within a single ferroelectric domain, we don't tend to see any anti-ferromagnetic domain walls. There may be some hidden in there somewhere, but in general, there doesn't have to be any. Okay, should I stop?
Yeah, no, go ahead. No. Well, in principle, actually, we have almost expired our time, but I wrote you already that we are a bit flexible, so maybe you can continue maybe for about 5-7 more minutes.
Okay, yeah, I have the opposite example, but if people need to go to their next meeting or something, I'm totally fine. I guess I wasn't, really a lot of questions and discussion, so I'm a bit too long. But I'll just quickly show you the kind of opposite example, again in the perovskite structure, because this is relevant to the question that was asked earlier. In the periodic table we looked at earlier, we didn't mention these rare earths, which have very localized F electrons. So in bismuth ferrite, we put the magnetism on the transition metal and brought the ferroelectricity in through this bismuth counter ion. What about leaving the transition metal to be ferroelectric and introducing the magnetism on the rare earth? And this is another approach. And I wanted to quickly tell you this story because it was a very fun one. So we designed a new material which had exactly this rare earth magnetism and D0 transition metal ferroelectricity, because I was approached by a colleague at Yale University, Steve Lamoureux, who said he'd like a material with these properties. He wanted it to be ferroelectric, but he wanted it to be switchable at very low temperature. He wanted a very large polarization. He wanted it to be magnetic, but not ordered at low temperature. So he wanted magnetic moments in there, but no magnetic ordering, even at low temperature. And so here, of course, as we discussed earlier, the rare earths are very good because they're really localized. They don't bond much with the oxygen, so they don't have high ordering temperatures. The environment at the magnetic atom had to change on switching, and he needed a lot of material. So a thin film was not going to be good enough. He wanted a bulk sample. And so the first question I asked, of course, was why? And he said he wanted to search for the electric dipole moment of the electron. And to a materials physicist, this was really interesting because I'd never even heard of the electric dipole moment of the electron. But he convinced me that this would be a good thing to search for. So, of course, we know that the electron has a magnetic moment, which is the axis of the magnetic moment is set by the spin quantum number. So I've made a little cartoon here of my electron with its spin angular momentum, and then it has a magnetic moment associated with that. What I learned is that the electron's also predicted to to have an electric dipole moment. And because there's only one quantum number in an electron, the spin quantum number, then the orientation of the electric dipole moment is also set by the spin quantum number. So once I have my spin quantum number, I have a certain orientation of the electric dipole moment. So this, of course, is very exciting because exactly what we couldn't do so easily in bismuth ferrite. In bismuth ferrite, we couldn't switch by 180 degrees the electric polarization and get the magnetism to switch. We had to use this trickery of it going around the different axes. In an electron, because the magnetic dipole and the electric dipole are locked to each other by the spin quantum number, if I switch the magnetic dipole with a magnetic field, the electric dipole has to switch. Or if I switch the electric dipole with an electric field, then the magnetic dipole has to switch. So the electron, in fact, is our perfect multiferroic. We didn't have to look as far as we thought we did. We have a multiferroic in the electron. And so this property that the electric and magnetic dipole and the electron are locked to each other by the spin quantum number, one can use to search the electron-electric dipole moment. And the way that one does this then is to switch the electric dipole moment with an electric field and measure the change in magnetization. So here's the experiment. We apply an electric field, and then just by the regular Stark effect, the energy for electrons with their electric dipole parallel to the electric field is lower than for electrons with their electric dipole anti-parallel to the field. So we get more, if you like, up dipole electrons than down dipole electrons, just by a Boltzmann distribution. Then we switch the electric field, and now we get more down electric dipole electrons than up electric dipole electrons. And when we do that, we measure the change in the magnetism that happens when we switch the electric field. The problem is the electric dipole moment of the electron is really, really, really small. If it exists at all, it's really tiny. And so one needed very special properties in order to be able to do this. So the idea was to have a ferroelectric material that was switchable, so we could do this switch. And it should have a very large polarization so that the effective electric field was really very big. It had to be magnetic, so it had unpaired electrons, but it had to not order. If it was all, the spins were stuck in super exchange interactions, say, they wouldn't reorient when the electric dipole does. One has to work at very low temperature so that the splitting is large compared with KT, and one needs a lot of atoms, so a big bulk sample to amplify the signal. One could still ask, why does one want to do this? And the reason for this is that various high energy theories predict very distinct values for the electron-electric dipole moment. It basically depends on how they incorporate CP violation into the theory. So for example, the standard model predicts about 10 to the minus 41 electron centimeters. We certainly weren't aiming for that. But at the start of this project, the limit on the upper bound that had been measured, or the upper bound at which the electric dipole moment would have been detected were it larger, was around 10 to the minus 27. And the Yale group thought with this new material, they could get down by about an order of magnitude. And if they didn't find the electric dipole moment between here and here, then they would be able to exclude all of these theories. So this was the motivation. Okay, so let me tell you very quickly about the material. Summary is we've made the material, we didn't find the electric dipole moment, otherwise you would certainly have heard of it. Okay, so we decided we'd take our ferroelectric titanium on the B side and put magnetic europium 2+ on the A side. So the kind of opposite design strategy to the bismuth ferrite. And europium titanate was known to exist, to be an anti-ferromagnet with a rather low Néel temperature, but to not be ferroelectric. And this we thought was because it has a very small lattice constant. And so there's just no room for the titanium 4+ to move off center. But we thought, okay, if we dilute the europium with barium, well, we'll suppress the Néel temperature, and maybe we'll make it ferroelectric because we know that barium titanate is ferroelectric and it has a larger lattice constant. So we'd expand the europium with the barium and it might become ferroelectric. So we made the material in the computer. It had the properties that we wanted. Our colleagues in Prague made it in real life, and it had the properties that we wanted. So here's the dielectric response as a function of temperature. And this cusp here is indicating the ferroelectric phase transition. And here we see the polarization as a function of electric field at different temperatures. And here's the magnetic permeability as a function of temperature. Remember, it had to have not ordered by liquid helium temperature, which it doesn't. So we wrote a nice paper about designing the material, and then our colleagues took it back to Yale to try to measure the electron-electric dipole moment. So here's the plot then of the upper bound on the electron-electric dipole moment as a function of time. And the red triangles are the atomic experiments on atoms or molecules, and the green ones are the solid state experiments. We'd hoped to get down to here, to about 10 to the minus 28 electron centimeters. Unfortunately, we only got to here. So we could claim that, well, we had the best solid state estimate of the electron, or search for the electron-electric dipole moment. But the material didn't perform as well as we'd hoped. And the reason for this was not that we didn't make what we had asked for, but that just it was not possible because of during the switching, the material heats up. And so it was not possible to precisely control the cryogenics, which was not something that we'd thought of ahead of time, but really, really reduced the accuracy. In the meantime, though, the ACME collaboration, so in 2013, reached a value down here, and subsequently have even gone almost an order of magnitude smaller. And so, again, here's the plot. This was the limit at the start of the project, and the limit now is 10 to the minus 29 electron centimeters, which means that all of these theories are either excluded or have to be extensively revised. So that was a lot of fun. This is my last slide now, which was some propaganda that came after we published our paper trying to measure the electron-electric dipole moment and not succeeding, which was from National Geographic Daily News, who were very complimentary and said that our new material, this was our europium barium titanate, might explain the universe's existence, the existence of matter, such as this astronaut seen above the Earth. And of course, I'm showing you this because it's very funny. It's a little bit of a joke. But I guess not entirely, because explaining our little corner of or some little tiny corner of the universe using our new materials is, of course, what I do for a living. And I hope I've shown you that the multi-ferroics and the transition metal oxides corner is an extremely rich area and fun area to be trying to do that. So thanks very much for listening, and I'd be happy to take any other questions or to go to the breakout room if we should go there to discuss whatever the organizers tell me.